Alright, for most of my explanation of what's going to be happening in the next, 3 chapters, you need to get this picture in your head. Now, in 6.1, we introduced the idea of a standard normal picture. Alright, that's the picture over here on the right. It's a normal curve, and very specifically, the mean is 0. The standard deviation is 1. Sorry, I made a mistake on that graph. Alright, the mean is 0, the standard deviation is 1. And you notice I have this other thing over here called z. Alright, now the standardized model we use, because we used to use tables and charts to look up all this stuff, we're going to be using the calculator for that. So I'm not going to go into detail about how to use these charts. We're using the calculator. But I want you to know that we can call the idealized world the standard world or the z world for when we're calculating z-scores. But for that world, the mean is 0. Our graph is in the middle of the x line. The standard deviation, the spread of the data, the variance, because square root of 1 is 1, is 1. Now, the real world information, more specifically what we're going to be looking at in 6.2 when we have the applied problems, where we're going to be doing most of our work for the rest of the class, the real world. Now, in the real world, your mean, your sigma, could take on any value at all. Your average could be, let's say, the average height of a female in America, which is 5'4", then it would be 5 feet 4 inches there. Your standard deviation, which I'm not sure what it is, but let's say it was 2 inches, your sigma would be 2. And your x value would be some target value from the real world. Now, what we're going to be doing a lot of the time, and for my explanation, the stuff that's going on in the background, is going from the real world into the idealized world to do our work. So in order to take an x value and turn it into a z value, do you notice that they're in relatively the same place? They are in the same place. But one is in the standardized world. How do you go there? You take your x value, you subtract the mean, you divide by sigma, and that gives you the z-score. Alright? Now, sometimes we're going to be doing things over in the idealized world, specifically if we're looking for what value corresponds to the top 10%, what value corresponds to the bottom 60%. We're going to get a z value from the calculator, but then we have to go backwards and get the x value that corresponds to the real world stuff. And that's going to be your x is equal to your z-score times sigma plus mu. Now, if you're clever, and I know you are, and very strong in algebra, then you recognize that these two formulas are the same formula. I just solved it for a different variable. If I solved for x, I'd multiply by sigma to both sides and then add mu. Oh, look, that's what x is equal to. If I solved for z in this other one, I would subtract sigma from it and divide by mu from both sides and divide by sigma. Now, I also want to point out something very important. This formula, this z formula, we're going to get in a couple different forms later on. When we're suddenly dealing with samples, then our sigma is going to change to sigma sub x, which we'll talk about in great detail when we get to 6.3, 6.4. And when we do the normal approximation of a binomial, right, we're going to use that a lot, especially if we're talking about presidential elections and polling, then again, these values would change, but it's always the same setup. Your z value is equal to whatever your real value is subtracted by whatever your mean is divided by whatever your standard deviation is. It's just that your standard deviation formula changes from one type of problem to another. But for now in 6.1 and later on in 6.2, this is the picture you need to have seared into your mind. This is what's going on in the background. And I will be making pictures like this to explain what's going on as we go from the real world to the idealized world, where mu is 0, sigma is 1,